Yeah, another draft physics video presentation. Physics girl again. Yeah. It's just such bad physics. So arrogant, so obnoxious. They're just, teaching, telling their little Jesus stories, and so, I'll do what's required, which is to counterpoint the preposterous fables of conventional notions of reality. Blah, blah, blah. And again, it's who's bad, really? Uh, the audience for falling for this crap are the crap spewers, who are so confident that these, and they're overtly non-explanations. I mean, they think they're going to talk about gravity. They have no clue how it works at all. Just the symptoms, just the consequences. Nothing about the internal mechanism. It's like looking at somebody who's limping. Could be limping because they have an infection, or it could be a bad joint, or it could be a broken leg. It could be lots of different things, and their guess isn't even close.
This is a candle inside of a completely closed box. We're about to drop it 11 meters and see what happens to the flame. Check it out. It becomes completely spherical. This may be...
Right, so like a water droplet, like anything, taken out of that context and put in a different context, it will behave accordingly. Yeah, there's not much to say. Yeah.
Isn't surprising. If you've ever seen pictures of candles in space, they become this eerie spherical shape. But wait, why should a candle in space and a candle falling in a box do the same thing?
So again, this everything has to be the same thing. Again, as I pointed out, it's just a silly notion. It's the forces act on us very differently, and when we're on Earth, we're not being acted on by one force. It's not just gravity. The other force is the ground pushing us back up. It's just a fact. Yeah. And they ignore it.
We're going to figure that out today. Hi.
You're really not. So you're going to talk about gravity as if gravity is the force pushing us back up, when that's not gravity. It's just not.
I'm Diana Cowan, and welcome to Lesson 8 of Diana's Introphysics class, also known as AP Physics 1 Review, also known as Physics by Diana.
La. So why would you have 3 names for it? See, they're physicists. They can't even organize something as rational as just having a name for a show. Oh, let's have one name for the show. That would make sense, wouldn't it? No, let's have 3.
Today's lesson is on gravity and orbits. And so we need to take
So she'll never even touch the subject of orbits in any kind of rational way. I mean, as I've pointed out, orbits are impossible, frankly, as a natural phenomenon, something flies in and it goes into an orbit. Nothing can ever do that. Nothing can ever go, 2 things can't meet each other and it just goes into an orbit around each other. It just doesn't happen. The fact is that gravity demands that they either smash right into each other, or if they miss each other, they never see each other again. And they have to hit something. Something has to change the equation to make it possible for them to find an orbit. Anyway, I won't draw it.
Through space.
Save it for later. Alright, we got this goofball crap.
Grab something nearby and hold it in your hand. I just so happen to have an apple, the object most closely associated with gravity and physics. I can feel it being pulled toward the ground. Isn't that kind of weird? I mean, there's no string here. There's nothing underneath. But
Alright, so again, they just keep emphasizing this pull, when the obvious answer is push. You can feel the extra push. You can feel its mass. You can feel the fact that it has electrons in it, and that those electrons are being affected by the same force that's pushing you down, and now you have more stuff pushing down. Pushing.
The object is totally being pulled toward the ground. Why? What is going on?
Well, you're not going to answer that question, so what's the point, right? You're not going to explain. See, I can sit there and I'll say light bulb, and I can explain to you inverse square law, right? I can say light bulb's doing the same thing as this hand, right? Okay, hand, I have the distance. The hand is 4 times bigger than it was here. Okay, so light bulb doing exactly the same thing. It's radiating the light, okay, in what could be understood as rays, little straight lines of photons coming out in all directions equally. And as I get further away, because the light is spreading both ways, this way and that way, it means that there's 4 times the area of the square that you're making, that the light is falling on. And gravity does exactly the same thing, so it could be understood as just the light bulb in reverse. Somehow energy is being consumed in the same way that light produces a source of light. So the sun radiates at the inverse square law. It behaves in terms of what it's radiating. The light is coming out exactly the way gravity's going in, right? So you can sort of figure out that it's exactly the same rule, then maybe it's exactly the same kind of mechanism. And there's no pulling involved.
If I hold up an even heavier apple, I can feel even more force. Why is that? Well, I'm going to tell you something amazing. Our answer to this question also explains how planets orbit the sun in our solar system, and even further lets us find extrasolar planets orbiting.
Right, so they have to talk about that, extrasolar planets or some other thing. You know, no. We don't find them because of gravity. Well, whatever, we find them because they leave a light signature. That is, they block light.
Stars throughout our galaxy, outside of our solar system. So by the end of today's lesson, this is what you're going to understand. You're going to understand how gravity, which is a force that makes an apple fall from a tree, it's also a force that makes stars, planets, moons, and even galaxies orbit one another. It's the same force.
So again, all this orbiting stuff, and the orbiting part is, yes, it's great. Gravity makes it possible for things to be in orbits, but orbits aren't something that comes from the outside. Something comes from the inside.
And we're going to use our new physics to describe mathematically what those orbits look like.
So new physics, it's 1919 physics, but we'll call it new physics. Yeah, and it's rubbish physics.
Like crazy. So, got everything you need? Snacks, calculator, spacesuit. The big idea today is
Right, so we're going to talk about what is basically a college subject in a juvenile, trivial way. Fantastic. I'm so excited.
Newton's law of universal gravitation. Let's go. This is Earth. Guess what all of those dots are, though? I'll give you a hint. They are not flies. These are all satellites. Yeah, fun fact, there are over 2,000 satellites up there. If you think...
Well, it looks like more than 2,000 little dots, but whatever. I didn't count. Don't really care that much, but okay.
That's a lot. Guess how many stars are orbiting the supermassive black hole at the center of our galaxy? I'll give you a hint. It's 6,000 times the number of flies on Earth.
So again, this orbiting thing in the galaxy is all based on some assumptions they've made about how these structures even work. Gravitationally, they don't even recognize the fact that it's not a sphere. It's a flat pancake, okay, which is a lot different than a sphere. And their argument is this thing is somehow getting smaller, not that it's getting bigger. It somehow are staying the same size. And so they have these assumptions about how fast stuff should be moving here on the outside. Oh, I have an arrow now. I can move my little arrow. They have assumptions about how fast all this stuff on the outside is moving, when all of it is not some solar system gravity. It's not like there's a sun in the middle and all this stuff is orbiting like a solar system. Not the same thing at all. It doesn't look like a solar system. It has balance. It has as much mass on one side as it has on the other side. It has lots of features that indicate it's not a solar system. So you can't use the same math because it's a completely different mechanism. And all of this little stuff out here could be going faster because, in fact, it's leaving. It's on its way out. It's just taking its time. Just as you could spiral into the sun, you can also fly right the hell out and in a spiral if you started in the middle. Can do. That gravity can cause. All right, so... pause for a second. Alright, should be back and such.
That's right. It is 100,000 million stars. All this orbiting happens because of gravity. So let's explore the history of how we even discovered gravity.
So again, all the orbiting happens because, frankly, I would argue it seems kind of obvious that galaxies have to start as binary systems. Two things have to be in proximity to each other, so they had to separate or something. It all has to come from inside somehow, and that's what the arms are basically the thing falling apart. The stuff is breaking out of the middle, not pulling crap in from the outside, and that's why the whole thing is spinning and there's lots of sense to it.
How we even got the idea of gravity. Imagine a time before we knew gravity existed, before we knew what held our planet, Earth, in orbit around the sun. Astronomers were perplexed. In the late 1500s, they didn't know about the orbit yet. They were just tracking the motions of the planets and the sun really carefully and being like, there are patterns, curious. And then eventually one dude suggested that Earth was orbiting this.
One dude. God. So bad.
Sun, which girl back then was a
which girl back then, huh? See, I mean, there's just nothing intelligent in this conversation. There's just no hope for it.
Blasphemous idea. That was Copernicus in the 40s, the 1540s, and it was a clear explanation for the patterns of these motions. And then another couple dudes, Johannes Kepler and Tycho Brahe, in the early 1600s, watched how all the
right, so it's just doing the Wikipedia page thing, blah, 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 blah.
planets moved and came up with a few laws to describe the planetary motion, but they still didn't have gravity. And then in 1610, Galileo used one of the first telescopes to look at Jupiter and saw, holy Europa, Jupiter has moons too! So by the mid-17th century, all these astronomers had a good understanding of how all these planets and stuff moved, but not why. Remember, with no gravity, it didn't make a whole lot of sense that Earth would orbit the sun, or that Jupiter's moons would stick around. That must have been baffling, until Isaac Newton came along. Newton's big idea? Gravity. There's this attractive force between all...
Right, so again, we're using the word attractive. I don't even think Newton cared, I mean, he really just didn't posit an explanation. All he's doing is explaining that there's clearly a force acting. Whether the force is pulling or pushing, I'm sure Newton could figure out that push would be the more rational argument. And Newton clearly stated that any imbecilic notion that this has any kind of spooky action at a distance. So in a sense, Newton was the first one to say spooky action. I mean, he basically discounted that as being no reasonable person could believe that it just magically happens. There has to be a mechanism, a force, a thing that's making it happen. And so Newton would find bent space the silliest of possible answers. I mean, he'd say, I could have said gremlins too. I could have said magical angels pushing with their wings, blah, 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 blah. I could have said that. I mean, and Newton actually did say crap like that, but he didn't write it. He didn't propose it as a real theory.
Objects with mass. Moons and planets and suns, apples and Earth. Yes, even between two fruit, there is a gravitational attraction. And Newton gave us a mathematical model of it.
Right, and the model, though, the big problem with his model is that the model combines the effects that two different things are having on each other. So it's like two light bulbs. He's just adding how much light there is altogether. So if I put two light bulbs next to each other, I can calculate how much light is hitting a spot. But the truth is, one light bulb's creating some light, and the other light bulb's creating some light. And his equation doesn't really get to that.
The gravitational force between two objects, F, is proportional to their masses, m, and inversely proportional to the distance between their masses, r squared. R is not the distance between two objects, it's the distance between their centers of masses, which for most planets is pretty much right in the center. And the constant of proportionality, that's just the number that we multiply everything by to make it all work, we call it big G. Look! This equation is so important it made it into the air. On our set. Big G. Now if you and I use this...
Yeah, that's very cute. Forgot that part was in there. It's just a constant to put things into, some sort of measurable standard. And that's it. It's not some absolute constant. It's absolute constant if you want to define what a Newton is. If you want to define it in some other terms, then you use a different constant.
Equation and we play a little bit, we can get some intuition for what it means. Let's try making either of these masses bigger. So if we make one of these masses bigger, what happens to the force? Well, it goes up. That means the force of gravity between me and Earth is bigger than the force of gravity between a pineapple and the Earth. And that force gets smaller as you move away from the center of the Earth.
Well, I would argue that the real simple way to understand it is that you're both doing something. Both objects are doing something. I create a change in the environment that other things are in. So if they're going to move because of that change in the environment, it's not going to have anything to do with me. It's going to have to do with the fact that I changed the environment. So if I create light, then obviously the light would shine on something, it would push it away. Now if I'm creating something called the opposite of light, the inverse, I'm taking light away. I'm taking the push away by absorbing it. The stuff that came from behind me, and the stuff that's coming from in front of me is also getting absorbed and creating the same effect behind me, and it's left to right is creating the same effect. Less comes out than went in. And that's what I'm doing to everything. And that's what I'm doing everywhere. So something looking at me is just seeing the fact that I'm a shadow. I'm a place that has less energy. And so one side is pushing them, the other side stops pushing them a little, and they'll move in that direction. Now, it doesn't have anything to do with me. I did it to them, but it's not going to make me move. There's not going to be some sort of, like, it's a rope between us, and whoever's the heaviest is going to get, whoever's the lightest is going to be moved by the force. The force clearly just affects him, and then his force affects me. His shadow affects me, my shadow affects him, but I'm not affected by my own shadow.
So if your R increases, then your force would decrease. In case you didn't know, you're not at the center of the Earth. You're standing a distance away from it.
So again, the same kind of formula could be written for a light bulb or anything else if you knew this G factor would be essentially the conversion. How well does the energy you put in, let's say, convert to photons out? And that would be your G, and the rest of it would just be this simple R squared equation.
Specifically 6,400 kilometers from the center of the Earth. So if you could move up out of the atmosphere another 6,400 kilometers up to here, then you are doubling your distance. So put you up here, looks like a man with a really big barbell. Imagine it's still you, up at twice the distance. So now you've doubled your distance to the center of the Earth. So you're doubling your R. So now you're dividing by a bigger R squared, and our model tells us that that would decrease the force of gravity between you and the Earth by a factor of 4. Because you're...
Right. Now, again, I can do this simple thing. She could just say simply, this is the effect, the same as my hand. Okay, all I do is move my hand twice as close, and it's 4 times bigger. So there, I've explained the phenomenon of the inverse square law. And again, a light bulb is doing the same thing to you all the time. If I move twice as close to the light bulb, I'll get hit by 4 times as many photons. So it's a rule of anything that's radiating energy spherically. Anything that you could reduce to, say, a point and say that's the source. And everything that does that, and everything like a light bulb does that. You could, just like they do with electrons and charge, I could take the light bulb and I could pretend, okay, that I'm going to make the point from where the light comes smaller and smaller and smaller and smaller. But I'd sort of be lying because the light bulb can't be converted into a point source. But for practical purposes, that's what it's going to look like. It's going to look like a point source, but it isn't really a point source. Yeah, that's probably good enough.
Squaring the two. That's what our mathematical model tells us. And guess what? It's true. Distance matters. A great example of this would be ocean tides. If the moon disappeared, what would happen to the tides on Earth? Would they go away? Actually, no. They would get smaller, but there's something that would keep them going. It's the sun's gravitational pull, which also contributes to the tides. But even though the sun is...
Right, and it contributes to the fact that the Earth is fatter at the equator than it is from the North and South poles. So, obviously that's going to affect how the water levels.
Much bigger, the moon is a lot closer, so R matters. All right, now big G. This is what we call the universal gravitational constant, and it's not...
So it's really about how much matter. So the fact that a center of gravity is created is really just telling you more about not a radius, it's telling you more about a diameter. So it's just about how much matter is between you and the thing that's affecting you. And you can draw a bunch of lines from you through the other object, and those lines average to the center of a gravity. But it's not what's really producing the gravity. Just like the light bulb, it's not what's producing the light. The light isn't coming from the center, some infinitesimally small center of the light bulb. It's coming from the surface of the filament or the surface of the LEDs or whatever's creating the light. And but you could draw the lines smaller, and you could draw them inside, into a center. But there is no center.
Number that we just measure, and as far as we know, it's constant throughout our universe. Is it different in some other universe? Could be, we don't know. But in our universe, it's...
whatever. Another universe. So why would somebody even throw in nonsense like that? Could it be another universe?
It is 6.67 times 10 to the minus 11. Let's do the units. On the left, we've got newtons for our force equals, and then whatever
but
the
this
units
is
are, G,
basically the simple to get
M
the
is
answer,
kilograms,
blah, blah, blah,
force of
blah.
gravity,
Don't need that.
F sub G. We're going to say the mass is 1 kilogram. So, simple. We know that the force of gravity is going to be the gravitational constant, so F.
So your size, okay, is going to be affected how much of the shadow hits you, so to speak. How much light would be coming from a source and would hit you would be dependent on your size. How big are you? How much light can you absorb? Now that's a surface argument with light. Light has to hit the surface, but with gravity, all you need to do is have matter that can be pushed by the gravity. So I probably need to draw this. It's just because electrons bang into electrons, bang into electrons, bang into electrons. So the force cascades through whatever number of electrons. However thick you are, you're going to absorb the photon longer for a longer period of time. So I guess it's worth drawing. So we'll do that. It's a little bit of a complex. This, yeah, that's what I need. All right. Now I should use my tool for this purpose. Blah 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 blah. Or not. All right. So we're somewhere over here now. Down here even. All right. So the U can be any kind of shape. All right, and you're going to effectively absorb a certain amount of light. And I could make you could crunch up into a little ball, all right? And so now we're really just comparing, it's the same U. So it really doesn't have just to do with the surface area that's exposed. It has to do with how much the energy is going to get absorbed by you, okay, in terms of how much element you have inside of you. So, you can either cause a small delay in the force. So let's say there's a force, right? The force is going to go through you and somehow be diminished coming out. It's going to be less than itself here. The point would be is that you can vary how much you screw it up because you have a bunch of electrons that just bang into each other. There's force between the electrons, and so they're just going to convey the same movement through all these electrons. Now, if you just hit one electron, that'll only absorb a small amount of time, you could understand. It'll only take a small amount of time for the force to move one electron to another space. But if it's moving a bunch of them, then that's going to take more time. So that's many units of time. So for each electron, you would consume another unit of time in terms of slowing down that force. And that's all you're really talking about, is how much force comes out in the end. So it doesn't matter what shape you are. It just matters how many electrons and protons do you have that have to be moved. And that's all that's going to decide. And it really isn't going to change anything about your profile in the sense that it will change in the sense that you're not a planet, so you can't just say, okay, everything got crushed by the gravity into a smooth surface. So it will make a difference in terms of if I'm really small, okay, I'm a flea. If you're a flea and you look at the human being, yeah, all different places will have different gravity. Just like on the surface of the Earth, a mountain on the surface of the Earth full of lead, let's say, is going to, if you're standing on that, you're probably going to sense, you're going to be experiencing more gravity because compared to other lines through the Earth, other straight lines through the Earth, that place has got more matter that affected the force going through, and the more matter being affected, the more gravity. Now, if I could bore a hole through the Earth, and you could stand over the top of the hole, okay, that area would have less gravity, because the only gravity that can affect you has to go through just pieces of the Earth, And the main part of the gravity that was going straight through isn't going to be there anymore, because there's no Earth below you. So technically, just as more matter on the surface could make it more gravitational, less matter, that is, being in having less matter between you and empty space out here. So it's all just about how much the empty space, however we draw that, right? Okay, clear space. Oh, shit. That's unfortunate. Everything was going quite well. And got ruined. Anyway, so it's just about how much exposure to the empty space you have and what you have in the way. So an asteroid that is funny shaped, will have more gravity this way because the force gets slowed down a lot more going this way than it does this way. There's only so many vectors here compared to the vectors here. But it really depends on proximity. The further away you get, the more it doesn't matter. So the further away you get, the more you can't see the profile, because really the further away you get, the less lines there are, that could be relevant, and it's just the same amount of matter. So it's only when you're close that you can't get these lines from over here. So you can't do the balancing it out thing. All you're getting is the lines you're close to. And so obviously here there's lots of rays you could draw that would still hit matter. When you're on this side, there's very few rays that can hit matter. Get that? Maybe you do. So we turn this one off and this one on.
So G is the gravitational constant times the two masses divided by the distance between them. The gravitational constant is 6.67 times 10 to the minus 11. Units are Newton meters squared per kilogram squared. And then the mass of the Earth, gotta look it up, but it's 5.97 times 10 to the 24 kilograms. That's a big old planet. And then the mass of our pineapple, 1 kilogram over, and then the distance between them. So that's roughly the radius of the Earth. So the radius of the Earth is about 6,370 kilometers, which is 6.37 times 10 to the 6 meters, because we want to work in meters for SI unit. We're gonna.
So again, there's only one force that's affecting you. The things that are falling. There's only one force. That's the force created by the thing you're falling towards. And your force doesn't move you. It can only move the Earth. So it's not like it's a contest, like I said, where you're pulling on the same rope. You're creating the atmosphere that something else is seeing. They're creating the atmosphere you see. So when we look down at the Earth, or we had gravity vision, we'd see something really dark, and we'd see something really light out up there, and obviously we're going to be pushed down because that's the atmosphere we're in. The Earth would see us as a little dark thing, but we're really, really small. So the amount of dark is so small compared to all the light that it's going to see above us and below us and left and right of us. So it's going to see a ton of other light. And like I said, when you're close to the Earth, all you're going to see is the black Earth. You can't turn your vision, and see any other part of the universe except behind you.
Square that, and don't forget to always work in meters so that the units match. And if I plug in all of these numbers and do the math, I get that the force of gravity on my 1 kilogram pineapple is 9.81 newtons. That's the force between this.
Right, so that's the blackness that everything sees. Everything sees the same amount of blackness. So it doesn't matter whether I'm an elephant or a flea. They look down at the Earth, they see the same amount of black. There isn't a different amount of black. There isn't a different difference. So they're all being affected by exactly the same difference in the field they're in. So obviously proportional, to the fact that that it's the same amount of change, and they'll move the same speed into that change. Because what's really getting pushed is just a single electron. So that the key thing is you just take a single electron, and you take the moon, and the single electron orbits at the same speed. The single electron has to obey the same rule. So it's just about how many electrons you have, electrons and protons. How many little bits of matter. And it's the little bits of matter that are really doing the moving. And they all see it the same, and they all feel it the same. So if you have more bits of matter, you'll catch more gravity, so to speak, and fall proportional to the number of masses you have.
Pineapple and the Earth. And remember, the force is a two-way street. So the Earth is pulling on the pineapple, and the pineapple is also pulling on the Earth, but the Earth doesn't really feel it. 9.81, that number looks fun.
So again, pulling implies, so that's the problem with the pulling argument. It implies that if a small thing pulls on a big thing, the small thing is going to move. If I take a rope and tie it to an elephant, and then I pull on the rope, who's going to move? Well, the elephant's not going to move. I'm going to move. And the point about gravity is that that's a bad analogy, because it's no way are the two things connected to each other. What they're doing is changing the environment the other thing exists in. So I can't possibly move because I'm creating gravity. My gravity can't move me. it's sending something. It's actually sending a shadow. The shadow can't affect me. The shadow's going that way. It can never get to me. It can't affect me in any way. It can only affect the other object. Yeah, that's the way to put it.
Familiar? We already know that objects near Earth are accelerating at 9.1 meters per second squared. So how did this pop out? Well, it's because F equals ma.
Unfortunate.
Is the threat real?
2 of them.
Yes, sir, we believe
Pretty
it is.
tacky. Very loud and obnoxious. Thank
And
you.
the force of gravity on a mass near Earth is gmm over r squared. So check it out. The mass of the object cancels out. And so
So isn't that convenient? Because she drew one of the masses big and one of the masses small, so then she could pretend to do, hey, I canceled this one out instead of that one out. When, she's really saying what's the acceleration on the small object? Well, the small object's acceleration is being created by the big object, so that's why you cancel it out. But if you wanted to know what the force was on the big object, what its acceleration is, then you'd cross out the big M. So, it's just sort of a deceptive to imply that it just depends on which one you're trying to figure out is getting moved by which object. And so, very deceptive.
then the acceleration only depends on g, big M, and r. So this is another way to show you that whether you drop a fish on a fishing pole or a slinky or an entire water park from a tall building, the objects will all accelerate toward the ground at the exact same rate. And if you plug in the mass of Earth and the radius of Earth here...
Right, and that's only because it's the same amount of rain. And all you're saying is, or there's the same amount of wind. And all you're saying is your mass, okay, is going to decide how big your sail is. But it's also deciding how much force it takes to move you. So those two things are proportional. So obviously the big boat needs to catch a lot of wind to move the big boat. The little boat needs to catch a little wind to move a little boat. But you're really just moving electrons and protons in the end, and they all move the same amount in the same amount of wind. So the wind is always the same. The little boats are all the same. They move exactly the same in the wind, and you're just counting how many boats do you have to collect wind. And so you know how much wind you caught based on how many boats you have.
mg, out pops a equals 9.81 meters per second squared. By the way, it's the center of mass of an object that accelerates at 9.81 meters per second squared. Check out this really cool video of my friend Derek from the YouTube channel Veritastic.
Well, I mean, that's just to see, they're using a slinky. It's already a loaded piece of energy. So it's really not going to show you the truth about this center of mass thing. And the differences in the amount of gravity, so this is probably worth drawing. Because this is an open question, because we don't have any good examples of things being affected by gravity differently. Well, I'll show this video first.
Dropping a slinky in super slow motion. Look at the bottom of the slinky. It almost doesn't move. It looks like it's defying gravity. But this
Right. Well, it's moving coincidentally at the same speed in the opposite direction of the gravity, right? So the force is equalized. The amount of spring pulling is pulling at the same speed that gravity is pushing. Sorry. The spring is actually doing something called pulling in a way. Obviously, it's an inverse of push, but anyway. Let's just play.
slinky is not a rigid object. It's collapsing, so the center of mass of it is accelerating down at 9.1 meters per second squared as the slinky changes shape. That looks awesome. But what does all this...
Too bad they stopped there. They should have kept going so we could see at what point the other end starts moving. What's this say about... Yeah, so it's a loaded object. So, it's sort of cheating because that's almost having little rocket engines or something. I mean, it's not a very good way of illustrating the fact that somehow gravity is always... doesn't have to go through an object. All right, so, it doesn't really get to this subject in a deep way, so I probably should just pretend you didn't mention it, but it's worth going over, I think. Where's my eraser? It's always something. Yeah. Pause just to find my eraser. Back. I have a bad habit, throwing things on the floor. Anyway, so the question would be, is if you were falling in gravity, well, Very long neck. Would you actually get stretched? Because let's say a very intense gravity where there could be a huge differential between your head and your feet. Because the real argument is that if you were an object, a round object, we know the gravity sort of has to come in, this end. It has to. It's not really a center of your gravity kind of argument. It's every bit of mass is going to be affected by the gravity as it travels through the object. And there's not really a differential here, okay, because this is the place the gravity has to go in. So it has to start there. And all you really can do is change how much time, again, is consumed by the amount of mass that it has to go through. So, I mean, it isn't like the gravity comes out of an object evenly. Some force is delayed a lot, and some force is delayed very little. And that's different than some idea of each level having a place. It's not like each level has a kind of gravity where you can affect things based on their level, because you can really only affect them based on how many electrons or protons they're going to hit. And their location is going to be irrelevant once the force hits up here. So technically the gravity is always going to be, you can't have a differential in your gravity at your head and a different gravity at your tail. So I don't think they'll ever see anything get actually spaghettified. They say that would happen. You'd get stretched because there's more gravity pulling you down here than there is gravity up there. But this is really the only gravity there's going to be, is what went in up here. So it's not going to matter what's down there. It's not going to stretch you. It's not pulling. It's pushing. And that's a big difference.
Stuff about slinkies and accelerations have to do with orbits. Here's what. The force of gravity that accelerates pineapples down toward the Earth is the same force that binds the Earth to the sun. This is a big idea. The law of gravitation applies across huge expanses of space and
So I'd explain to you why the slinky didn't move. The bottom of the slinky didn't move. It's because the gravity hadn't gotten to it yet. That's the simple answer. It takes time for it to go through the object. And because the object has a spring in it, it takes even more time. And there's also that spring's pushing up the opposite way, but whatever. The point is that it's a pushing force, not a pulling force. And so in a sense, that slinky thing should tell them, hey, maybe this idea of spaghettification wouldn't actually happen.
Explains why massive planets like Jupiter.
Oh, hold on a second. All right, I think I'm back. I don't know where we were, but we'll catch up.
Stay in their orbit around the sun, even though they're really, 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 really far away. Let's analyze an orbit. It's a pretty neat idea. And actually, the more you think about it, the more confusing it gets.
All right, so it's really not that confusing, but there are rules. And again, one of the fundamental rules is stuff just doesn't get into orbits by just flying into an orbit. You can't just fly into an orbit.
Think about the International Space Station. So it's up there at about 400 kilometers above Earth's surface. So let's draw that. Actually, 408 kilometers above Earth's surface. If we had just put it there, it would fall straight down. But if we gave it a sideways velocity, well, it might fall in that parabolic shape that we learned about in ballistic motion episode. If we give it a massive...
All right. So again, I think the more important thing to emphasize about gravity is the fact that it is conservative. Okay, so how much light you see going out or how much light you see going in, it's the same amount. So the amount of pushing you're getting going into the shadow is the same as the amount of pushing you got to do to get out of the shadow. So, jeez, remember these things. Must hit this button. All right, so if there is gravity, there's a thing, it's gravitational, and you're way out here. The fact is that you're pretty much doomed to just crash right into it. So we can play this game, velocities and all this kind of stuff, but the idea is you're going to crash right into it if you're far away, because you're going to get bent and you're going to turn and you're going to crash into the object. Now, if there's a special case where you have enough velocity and you fly by, okay, there's this idea that all it's going to do is bend you and then you're going to leave. Okay, there won't be anything close to an orbit. You won't go around twice. You won't do anything like that. You'll just go in and you'll go out, because the same energy that's attracting you is going to be the same energy that's going to be releasing you. So you'll be gaining momentum as you come towards the object, and it doesn't matter whether you come towards it there, or you come towards it here. It doesn't matter where you come towards it. If you don't hit it, you leave. Okay, you just don't stay. And the only way you can get into an orbit is somewhere on this path you need to get hit by something. Something has to be in your way, and it has to kill some of your velocity. So some of the velocity that was created by the object has to somehow be taken away, so now you can collapse into an orbit. But that's the only way you can ever get into an orbit, is that something has to collapse your velocity. Something has to kill it. Because the fact is you've gained enough velocity to leave. And that's what you're going to do. So if I'm throwing marbles into the gravity well, all right, the illusion is that they have friction, so they slow down. So that's why they don't do what I'm saying. So if I throw marbles in a gravity well, they don't just either hit it or fly out, right? They don't go through the center or fly out. But that's what they would do if I could make it frictionless. I could just drop the marble on the edge, and it would just go right out and fly out the other side. It wouldn't fly out the other side. Actually, it would slow down, go right on the edge, and then, tip over. But that would be its doom. And then if it didn't go out, if it didn't stay right on the edge and then fall back in, it would fall in, well, frankly, with the same velocity it had the last time. So it's either going to have a trajectory that's going to mean it's going to terminate in the thing that's causing the well, or it's going to leave. So orbits are a special case, and I would argue that they're more likely to be created by stuff separating from a center than stuff entering from the external universe. All right, continuing. Oh, I was continuing. Yeah, I don't know why I said that. I thought I had to unpause.
Huge sideways velocity, then it might fly off of Earth and out into space and never come back. But a just right amount of huge sideways velocity, and it'll fall around Earth and keep missing. And that's how you get orbit. An object in orbit is in free fall. We saw evidence for this with the candle in the box.
So again, she just sloughed over the idea that, but you can't do it. Like I said, you only have two choices, and so you have to interact with some other matter to slow you down to stay in an orbit.
The candle looks just like a candle orbiting the Earth on the space station. They're both in free fall. The only difference is that one is moving sideways fast and the other is not. So the ISS is falling around Earth, and that orbital motion could be circular, like I drew, but orbits don't have to be circular. Comets, they orbit in very eccentric ellipses, but most planets and most moons orbit in ellipses that are pretty close to circles. So, hey. And
so again, the comet only is in that orbit. Let's say the comet is actually from some other piece of space, the external universe. And I would argue it's probably more like the other way around. It was junk spewed by the sun that's just trapped like a moon. But anyway, it had to hit stuff, so it hit something, which seems logical enough that it would hit something in the early universe, early solar system. So in the early life of the solar system, there was lots of junk to hit, so it hit something, and that's why it's stuck.
Circular motion. We have a tool for that. The sum of the forces on an object moving a circle will be mv squared over r. And what is this force? Well, it's the gravitational force between the ISS and the Earth. So that, gmm over r squared. Look, the masses cancel again. And we get an equation relating the sideways speed that you need to orbit a big old planet with mass m at a distance r from its center. We've got a v squared. We're going to cancel this r with one of these. And we're going to have to square root to get rid of that. So we'll end up getting v equals the square root of gm over r. So this is our equation for orbital velocity based off of the mass and the radius of the thing that you're orbiting. The mass.
Right, so the mass that you have doesn't matter anymore. So that got crossed out. So again, it's just an effect being created, and what it's really saying is what are your subatomic bits doing? So the simple argument I would make that physics should be pointing out to everybody is that gravity is a nuclear force. Gravity affects electrons and protons. It really doesn't affect you. It doesn't have anything to do with you. Okay, yeah, you're a byproduct of what the electrons and protons are doing, so obviously it affects you. But I just mean it's not something affecting complex matter. It's really pushing electrons and protons, and that's all it's pushing or pulling, if you want to look at it that way. But that's what should be emphasized, is those are the bits being pushed and pulled. And obviously they're all the same size and they're all the same, so the effect is going to be the same on all of them. And so you're just saying, how many little boats do I have, and that'll tell me how much wind I caught. How much wind I need is completely dependent on how many boats there are to push.
This is cancel. So the mass of the ISS doesn't affect its orbital velocity. It better not, otherwise when astronauts stepped outside to do some repairs, they would have a real problem. So what is the sideways velocity of the ISS? Let's work it out now that we have the equation. Its height averages about 410 kilometers above the surface of the Earth.
We'll jump ahead a little because we don't need to really know this, do we? No. It doesn't have anything to do with theory.
Space station around Earth. That's pretty cool. If you actually go and search on the internet for the orbital velocity of the ISS, you get 7,660 meters per second, which is awesome.
Which is the same exact thing you just did. They're not measuring it with a speedometer or something. They're doing the same calculation you did to figure it out. It's a assumption, frankly. And yes, you can time it. You could actually time how long it takes to go around, but then you have to know exactly how high it is. So again, there's always something that they're just assuming.
But we just worked it out from the math, and you get the same value as you would search, and that it actually is in reality. That's really fast. Almost 8,000 meters per second, 8 times 10 to the third meters per second, but not quite as fast as the speed of gravity.
So she could have put in something that means something to everybody, right? Instead of this meters per second, she could have said it's 17,000 miles an hour, which I think it is.
Waves. I'm gonna go off on a little tangent here. So it's something.
So this is the parts. This is just precious. Gravitational waves. So they have no clue what causes the effect. So they haven't advanced from Newton at all, in the sense that this is all Newton, right? This is all stuff Newton had already figured out. So she hasn't demonstrated that they know anything more than Newton knows. All right, Newton said, I can tell you what it does. I can't tell you what it is. So, we're 13 minutes through the video. She's on a subject of gravity, and she hasn't stepped beyond the completely vacuous statement that Newton made, which is, I have no idea what's causing it. And they have no idea.
Violent happens, like two black holes collide, you can get a gravitational wave, this ripple in space moving across the universe.
So just more mush, okay? This wave created by what? The change of the position. So the two things are going around each other, and so that this is subtly different than this. And it's only subtly different. It's a tiny difference between what you'll see at a distance, and especially what we can see, right? We can't see those two objects at all because they're so far away. We don't have any of that resolution, and there's no reason to assume that gravity is somehow different than photons or anything else in terms of the resolution it's possible to discern. And that's all you're really saying is the difference between this and this, this and this, and they're saying that's a wave. And again, it's like two light bulbs, doing this with two light bulbs, the amount of light that hits you. But they're light bulbs that can shoot through each other. That's the theory, And so this is a little more spread out than this. So the center of the light is a little closer this way than this way. But it's a tiny difference. Insanely tiny difference. Alright, pause for a moment. Alright, should be back. Alright, so this whole gravitational wave thing, again, the evidence is unobtainable in terms of any kind of hard evidence that we can all see. All we have is some group of physicists paid billions of dollars, wasted, all that kind of stuff, lots of money invested in something, and they have every incentive to force it to work, even if it doesn't. So, but that's all you really have. And you have Einstein basically saying, yeah, I don't see any way you can make one of these waves that would ever get anywhere. So there was no Einstein theory that you convert matter into bent space, right? We're saying bent space is the cause of gravity. Bent space is what the wave would be in, and yet somehow they convert actual matter, actual electrons and protons, into bent space. So they make the electrons and protons into wind, is the analogy, right? So you have sailboats, you grind up the sailboats, and somehow the sailboats turn into wind. I mean, it doesn't make any sense. It's just made up, and it doesn't happen. And again, LIGO is full of impossible thoughts of you're bouncing a light 1,600 times back and forth between mirrors, 2 miles away from each other, back and forth, 1,600 times. And then you're going to tell me that you can measure how far that light moved, how far it progressed in space within 1/10,000th of the thickness of a proton. You can't even figure out how many atoms the light hits going into the mirror each time. It's atoms worth of difference. Each time you hit the mirror, there's atoms worth of difference. And yet you're going to measure 1/10,000th of a proton. It's a ludicrous statement. It's a certainly extraordinary claims that should be backed up with some kind of evidence, something they could show me. And they don't show you anything.
And that moves at the speed about 3 times 10 to the 8th meters per second, which might sound like the speed of light to you. And in fact, gravitational waves do move at the speed of light. So that's 10 to the 5th.
Gravity functions. It is the shadow moves at the shadow that is gravity, right? The absorption, the fact that I have that energy isn't getting to you, notice of that will move at exactly the same speed as all the energy in the universe. That is magnetism, light, gravity. You want to make up something about electricity, you can, but electricity really has nothing to do with it. There's no electric field. But you could argue charge. They all move the same speed. Charge, magnetism, light, gravity. It's all stuff moving the same speed. Now, why would you think it's different stuff? Why would you think one part of the stuff is some sort of bent space and the other part is some sort of field perturbations and all this? Why would you do that? Logically, no good reason to do that. Just bad reasons to do it.
Times the orbital speed of the ISS. It's very fast, but this is impressive also. Okay, let's move on. So now you have a tool that can tell you how fast you need to go in order to orbit a mass at a particular distance from its center of mass. Here's the thing. It's kind of hard to tell how fast you're going in space. We don't exactly have mile markers. So what if we could...
Well, we sort of do, which is, again, we don't have mile markers. You can say just any old star that you know is close to us, so you just use Alpha Centauri or some other reference, and you just say you can see how much your angle deflects or changes in terms of what you're seeing, where you see something. And so, again, we have lots of mile markers. So getting out of the solar system, you got them all over the place. All the other planets are good mile markers. They'll tell you exactly where you are in space by just referencing them. So it's almost like saying we can't navigate the oceans when they use the stars to just navigate the oceans. We use the stars. Well, why wouldn't you use the stars if you were moving through space, right? I mean, they got pretty exact understanding of their position in the middle of the Atlantic, on these little wooden boats, by just knowing where the stars are supposed to be, and knowing that tells them where they are. So that's kind of a dumbass statement for somebody, a professional physicist, to make. I mean, that's kind of a dumbass thing to say. Oh, in space we can't tell. Yeah, we can.
Rewrite our equation to tell us something more useful, specifically the time that it takes you to orbit. So start with our orbital velocity equation. We'll write it like this. We're going to just square that and get v squared equals
we'll
g
move ahead
over
again.
r. And then recall that we're orbiting in a circle, which means that the distance in one complete revolution, it's equal to the circumference of the orbit, or 2 pi times the radius, r.
Right.
And it's easy to measure the time it takes to complete one orbit. So we'll call...
And the pi thing is important, like to the two-slit experiment. Yeah, see, 2 pi for the whole circle, 1 pi for half the circle, 1/2 pi for a quarter of the circle.
That orbital period, the time, big T. So that's our orbital period. So the velocity turns out to be easy to measure in terms of the distance traveled in one orbit, 2 pi r, and the orbital period T. So our velocity is delta x over delta T.
Right, but you have to know your distance, and you're not going to know that, so you're going to have to just make it up, frankly.
Equals 4 pi squared r cubed. You may have seen something like this before, stated as Kepler's third law. And in fact, Kepler did observe this relationship empirically in the sky, and then Newton showed us how it worked.
So again, he doesn't show us how it works. So again, this is beyond pointing out that it works because there has to be a force of some kind. And that's what Newton said. There has to be something that's doing it, okay? But yeah, I don't know what it is. But this is what it does. And, I think Newton could have imagined the whole mechanism if he knew what electrons and if he knew what atoms were. He would have been able to figure out that, yes, all you're talking about is moving electrons and protons, and you can do that with an external force without running into thermal problems or other kinetic problems. It works kinetically because there is no friction with electrons and protons.
Is a fantastic tool. This is the mass measuring tool that I promised you. Check it out. If you can observe how long it takes a planet to orbit the sun, for example, and if you can find the radius of the planet's orbit, that's r, so that would be approximately the distance from the sun to the earth, then you can calculate the mass of the sun. You can measure the mass of the sun. So let's do it. The Earth's orbital radius.
Right. So this is just taking the same relationship exists, and you're just figuring out different ways that you can just convert it so you can find any variable by knowing the other variables. Okay. Anyway, I might as well just play.
Yes, r is about 150 million kilometers, so that's 1.5 times 10 to the 11 meters. So we've got 4 pi squared times 1.5 times 10 to the 11 meters cubed, which equals 6. In terms of Earth masses, that's about 330,000 Earths worth of mass. We just weighed the sun. That's so cool. I bet you didn't put that on your more.
So I say a million times, so I'm really not. I'm cheating a little. So it's 368,443 whatever times heavier than the Earth. But again, its size is insane compared to the Earth. So its density is really thin.
To-do list. Astronomy is amazing. There's so much we just did and that astronomers have done with just a few different tools. Just like we did, they determined the mass of a supermassive black hole at the center of our galaxy.
All right, so just what we did, blah, 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 blah. And it's not just what we did. And again, it's, so they say it's a black hole. They don't know whether it's a black hole or just a big giant neutron star. It could be. It doesn't have to be a black hole. We can't see things that small. So, we know that there's a place in space that would be a light year across, let's say. And we know somewhere in that space that's a light year across, big space, big amount of space, there's a mass, okay, that totals, 1 million suns. So what? It could be this big, it could be that big, it could be lots of sizes inside of there. It doesn't have to be a black hole. So, again, they haven't proven the existence of black holes. And they certainly haven't disproven the fact that it could be a neutron star.
Using Kepler's third law on the stars orbiting nearby the supermassive black hole. And my favorite use of these tools, astronomers realize that there's mass out there in the universe that we can't see. It's called dark matter. In the 60s and...
So she just made this part up too. So because, again, the galaxy argument. So first, they're not acknowledging the galaxies are flat. Okay, and they're not. You don't use spherical gravity laws for something that's flat. You really don't. It's just not. It's not the right thing to do. And then it's flat, but it's equal amount of stuff on both sides, and there's a lot of stuff in the arms of the galaxy. So obviously that stuff is gravitationally affecting the stuff on the other side. If there was an opposite Earth, a Vulcan, on the opposite side of the sun, the same as the Earth, and we just made those planets really, really heavy, and we made the sun really, really light, they'd still be able to orbit each other if they were doing that, okay, as a binary system. So you could take the sun out, you could pluck it out, and those two things would orbit each other as a binary system. So, and that's what galaxies are doing. The arms are rotating around the other arm, okay? They're not rotating around the center. And so the gravitational equation is much different than some traditional all the masses in the center sun kind of perception of the reality. And that would explain it. You don't need any dark matter then.
70s, an astronomer named Vera Rubin measured how fast stars in spiral galaxies were orbiting around their centers, orbiting on the center of the galaxies. And she found that the stars on the edge were going much faster than they would have expected based off all the stars and things that we could see, which meant that there had to be tons of mass in these galaxies that wasn't emitting or reflecting any light.
Right. And so this is all based on the assumption that they're in a perfect orbit, which you have no reason to assume they're in a perfect orbit and that they're not either moving in or moving out. Now, if they're moving in, they would be going slower. And if they're moving out, they would be going faster. So there you go. And the galaxy has every appearance that it could be moving out. There's no There's no clues. It doesn't sit there and tell you, I'm contracting. I'm pulling stuff in. Pulling stuff in and letting stuff out are going to look the same. And so they're just, again, assuming. They're just making some assumption that, oh, it can't possibly be falling apart. Where, yeah, it could possibly be doing that. It's getting bigger. If it's getting bigger, then the bits on the outside have to go faster because they have to go further away.
Called it dark matter. And since then, astronomers have found lots and lots of evidence for dark matter, and they've realized that it's...
They really haven't. And the evidence is it fixes all the other stuff that's broken. So the stuff that doesn't make any sense, like their silly gravitationally lensed images that don't make any sense, they're mathematically uneven, disproportional, sloppy, ugly, well, we can fix those with dark matter too. That's what they found. And so they're using the fact that it fixes all their mistakes as evidence that it's the right answer. When, no. It's another wrong answer, and you're just piling on your wrong answers. You're just piling one wrong answer on top of another wrong answer. So you're really talking about now the tuxedos that your gremlins are wearing. Well, if the gremlins wear tuxedos, then they'll be able to get through the bouncer and be able to get into Club 57 and blah, 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 blah. You're just telling a silly story and making up crap as you go along.
super common. In fact, it makes up about 23% of the mass in our universe. And
so again, just this isn't physics. This is, I mean, really, they should make a distinction between the stuff you know, like the Newton stuff, really good, reliable, hard facts, and the crap they just pulled out of their ass. Oh, 23% of the universe is, mush. That, super material that we've never seen before, and none of it's here, and we can't analyze it, and blah, blah, blah. It's magic. Gremlins. It's gremlin sauce.
Still have no idea what it is. We've ruled out like dark planets and like dead stars.
And, what? Pixie poo. Okay, it's not pixie poo, it's gremlin poo.
We don't know what dark matter is yet. And we learned all of that from GMT squared equals 4 pi squared r cubed. But
pitiful.
There's more. I want to give you a quick peek at some really mind-boggling physics from the theory of general relativity.
Okay, so we're 18 minutes into the 23 minutes, and she's finally going to get to the modern theory that she was claiming she was talking about when she really wasn't. She was just giving us Newton's equations.
Which is Einstein's theory that gravity can actually bend light. So when I first heard about Einstein's theory of relativity, I was like, wait, so all of that stuff I learned about Newton's laws is about gravity is wrong? And no, that's not quite true. It's just that...
Oh, okay. So at least she's conceding that, yeah, there's nothing wrong with Newton's observations. And the fact is, Newton said, I don't know what's causing it. So obviously it's hard to say Newton was wrong when he said, I don't know. Yeah, when he proposed the I don't know theory, he couldn't exactly be wrong. But when Einstein said, I think I do know, and he said, bent space, I mean, that's just too silly. It doesn't explain anything. It wouldn't be an explanation for a light bulb. If somebody said, well, the light bulb has an inverse square law because it's bending space, you wouldn't fall for that.
Newton's model is not quite as precise as Einstein's model, but Newton's model is really helpful in most situations we're dealing with.
So again, it's not a model. It's just some math describing effects, and he doesn't, what's the word he does? He doesn't venture to speculate on, cause.
Einstein's more precise model says is this. In an earlier lesson, we said that the mass is the measure of the inertia of an object. So, for example, this cow, and the mass tells us how hard we need to push it to accelerate it.
Again, so, the fact is you have to push it to move it. Yes, that's right. It doesn't move until it's forced to move. So that's the simple statement. Things move when they're forced to. That's it. Matter moves when it's forced to. It doesn't move when it's not forced to. It doesn't have any power to go anywhere when it's not forced to. So it just depends on what's forcing it. That's where it'll go. So whatever the force says, the matter does. And when the matter does that, it changes what the force is going to do to other objects.
F equals ma. So that's what we call the inertial mass of an object. And now we've seen that the mass of an object also determines how much gravitational attraction it will be between it and other objects. So
now we know that how much attraction is dependent on how many electrons and protons it has. It's no more complicated than that. Just count how many electrons and protons it has and you have solved the problem. Yes, neutrons, but neutrons are technically protons and electrons.
F equals gmm over r squared. The m in there is the object's gravitational mass. And when we derived little g earlier, we set those two forces equal to each other, and I did this in my physics class, and people have done it for centuries, and we canceled out the m's. But think about it for a minute. It works. But should we be able to just do that? Why are inertial and gravitational mass the same thing? Why is...
They're not. But there's only one mass. That's it. And you have to move it with a force. So there's no point in comparing. Well, yes, when you're moving it with a force, it moves, and when you don't move it with a force, it doesn't move. Yeah, duh.
The m that determines inertia the same as the m that determines what gravity it feels? By the way, I didn't wonder this until after I finished my degree in physics. It's kind of a mind-blowing question. But enter Einstein. One of his many huge contributions to physics was...
Okay, so this is just so bad, but whatever. No, this is one of the big detours physics took. And one of the first big detours. Einstein gets away with this, and then Bohr gets away with his crap, and everybody just gets away with a bunch of completely unevidenced speculation that isn't very deep, that isn't very thoughtful, that doesn't go nearly, isn't very well tested against counter arguments.
Idea called the equivalence principle. He stated that the...
Yeah, so the idea is silly, that all interaction is equivalent, and it really isn't. Interactions are very circumstantial. And again, hitting you with force with a bullet and hitting you with force by throwing a bag of feathers at you are going to affect you differently, very differently.
effects of a gravitational field and the effects of accelerating motion are identical and cannot be distinguished.
Yeah, so they always can be distinguished. Again, if you just have a window and you can just look outside, you'll be able to see when you're moving and when somebody else is moving. All these questions will be answered in easy ways to answer them. So again, it's just more garbage. I mean, Columbus didn't have any delusion that the, North America was sailing towards him. He didn't get in his boat and say, I'm going to just sit in my boat and wait for North America to crash into me.
Whether you're sitting in your bedroom on Earth in a gravitational field, or whether aliens have kidnapped you and put you on a spaceship accelerating at 9.8 meters per second squared, you would not know. You wouldn't notice any difference.
Yes, and if you were accelerated by gravity or any other force that applies its effects to you subatomically, you'll never feel a force that affects you subatomically. So any force that affects you subatomically imposes force on your bits, your little bits, you'll never feel it. If it has to go through your cells and your atoms and your compounds and all of that structure to get to you, then you're in big trouble. Then you're going to feel it. It's that simple. It just has to do with the force that's moving you. So if I can create a force like gravity, like magnetic force or some other force, you won't feel it giving you velocity either. You won't feel yourself being accelerated by it because it won't accelerate you unevenly. It'll accelerate all of your parts equally, substantially equally, and therefore you just won't feel any of it because there won't be anything moving differently. Your feet won't be moving faster than your stomach, for example, so you won't feel queasy or uneasy or any of that kind of stuff because the effect is going to move all of your parts at exactly the same speed, and therefore all of your parts are going to feel quite comfortable.
And how apples fall or how heavy you feel, because in a spaceship, your apple isn't actually...
Pause for a moment. Alright, should be back. It's kind of dangerous playing with this pause button, but anyway. I am a risk taker sometimes. This should be what I want. Yes. Okay. So, just for clarity, this all can be reduced to something very, very simple. In terms of there's force in the universe, we could call that the lights. The lights are on in the universe, and the objects are the sinks. The objects are basically the light goes in, and it doesn't come out right away. Okay, it's delayed in its progress. Okay, so you can just understand it has to hit an electron. It hits an electron. Let's say it hits one electron. Let's just draw that over here. So there's an electron, and it hits this electron, and it's moving this electron. Obviously, when this electron moves, it's connected to other electrons by the same force. It's bouncing back and forth, let's say. And so what it's really doing is just conveying the motion to the other electron. Right, and then that electron moves, and then the other electron moves. So you're just moving an electron. It's the same electron essentially, right, or a different electron. It doesn't really matter. You're moving it. And how much movement what's the total amount of time? So any one force bit goes into an object. How much time? An object would be something made of a lot of electrons and protons and neutrons. how much time does it spend pushing electrons or protons or neutrons? How much time does it have to occupy? So you're really just saying how much is it delayed coming out, all right? Because that's all it comes down to in the bottom line. And the delay means that it covered a distance. So the distance from when it went in to where it comes out, okay? If you calculate the distance based on the time, right, you'll get a distance that's much larger than what it actually did. I mean, a distance much less than what it should have done. So if I calculate how much distance it should have covered, it didn't cover that much distance, it covered much less. So that means it has less velocity. That means it has less momentum. The point is I'm changing its momentum. By absorbing it, by forcing the force to force objects to move, the force loses momentum. So it comes out at a time it's too late, and it's way behind where it should be. It should be here, it's way back here. That's a change in its overall momentum. So that's why more goes in than it comes out of the object, and that's the simple explanation. The force loses a little momentum when it has to go through matter and move electrons and protons. That little bit of loss of momentum is what you're being affected by. So the Earth is a sink. Now I'm going to feel, if I'm standing here, what the universe, the energy coming from the other side that would balance me, that would keep me in equilibrium, that energy isn't going to be equal, because the Earth is going to take a little bit of the momentum out of the force coming this way, and now I'm going to get hit with more force this way, momentum, and I'm going to move into the Earth. And it's going to be completely proportional to how many electrons and protons had to be moved. That's going to tell you how much momentum was taken out of the force. So unlike what they could understand back in Newton's day, this particle model works because there is no heat, there's no anything. I mean, there is some heat. Obviously, you're moving electrons, and everything we know is hot. So that makes sense. The Earth is molten in the center. What do you think is causing that? Well, the good explanation is the gravity is causing that. The actual fact is that the matter in the Earth is moving in both of these directions and causing lots of tension and action. So the movement of the electrons is actually causing a lot of disturbance inside of the Earth, and that's what's making its center liquid. I mean, a simple explanation works as long as you understand it's just about force, little bits of momentum, and matter bits. And that matter doesn't move until a piece of force the wind has to hit the sail. And when the wind's hitting the sail, what's happening to the wind? It's not getting where it was going, right? That's the whole point. It's really that simple. You don't need any of this other crap. This religion.
Falling because there's no large gravitational body around to pull the apple. Imagine instead of dropping an apple, you shoot a laser beam across your bedroom in the alien spaceship. The laser.
So this is the hilarious part, right? So you imagine that and you say, yeah, so that can tell me exactly how fast I'm going. So she just said how we can't tell how fast we're going. We can't know anything. We can't do a physics experiment that'll tell us anything. And now she's doing a physics experiment that'll tell you completely how fast you're going. It'll reveal who's going. If I have two people passing each other in spaceships going half the speed of light, how can I tell who's moving? Well, if they just do this experiment, they'll both be able to tell exactly how fast they're moving. So problem solved, right? I mean, this is an overt paradoxical non sequitur. You can't. Contradiction is one of the things you're not supposed to be doing. You're not supposed to contradict yourself. You're not supposed to say in one sentence you can't do any physics experiments that'll tell you how fast you're going, and then say, well, what if I do a physics experiment that'll tell me exactly how fast I'm going? It's too stupid.
beam shoots in a straight line through space, but like in the Apple example, the spaceship is accelerating up into the laser beam. So by the time the beam has reached the other side of the room, the spaceship has moved and the beam will hit a slightly lower part of the wall.
Right, and depending on how fast I'm going, I'll know exactly how fast I'm going. It'll be a speedometer. It'll tell exactly how fast, how much that little light dot drops will tell me exactly how fast I'm going. Now the trick is I'd have to have a very, very wide, LIGO style 2-mile spaceship or bigger. I'd have to have a pretty gigantic spaceship to be able to see that, okay, to see the light moving down. So that's the only downside, is light moves so fast that it makes a really lousy, it just doesn't, it's hard for me to make it into an instrument that'll tell me this truth. Now with mirrors, maybe I could do it, but the problem is the way the light is emitted is just as broken in this analogy as everything else they'd say, right? So this all assumes that you can make an emitter of light, okay, that isn't broken by the very speed that you're attempting to detect. So I would argue that even if you could do this, you can't do this, right? So even if you attempted, even if you could get up to half the speed of light, and even if you could do this experiment, the big flaw in it is their lack of understanding about how photons are, even what a photon is. They don't know what a photon is, just like they don't know what gravity is. So the problem would be is that the spaceship's moving, okay? So we're talking about surfaces. So the surfaces are moving, and the simple idea is you send the light across here, and by the time when the light left the spot was here on the wall, and when the light gets here, the spot's going to be down here, in the sense that this new spot is going to be the spot it's going to hit. So you'd have, you're going to have a spot on the wall. It's going to hit the spot that you want to hit is going to be up here. So that's what you're going to see, is that the light's below where it's supposed to be. But the point is when you're emitting the light, this side is moving. So the problem is the light's a composite object. The wave, even if you want to believe in the silly wave theory, the wave is a composite. And the problem is that your wave now is getting spread out. So what's happening when you're shooting your photon is the first bit of the photon leaves, at the right position, but the next bit's going to leave way over here, and then the next bit's going to leave way up here. So what you're doing is you're separating the little bits of the photon. So where the photon had to have a polarization that was this big, like the separation was this, now you've converted the separation into this monstrously big separation. And so you can't even see that, but it would, you're dramatically sending the photons now over a much larger distance. So the photon would show up on the wall in pieces, that are very far apart from each other. So there wouldn't be any realistic hope that your photons now are being spread over so much surface that you wouldn't be able to receive them as photons anyway, because now you've changed their polarization. You've stretched them tremendously. And it might not even be in the direction of their polarization. Their polarization might have been this way, and now you're creating distance between them in this direction. So now you've created two polarizations in the light. So there's very unlikely that you're going to be able to receive the energy as a photon. But anyway, these are all parts of this reality that they just slough over. They just pretend they don't exist. Like I said, the length of a photon, they just never paid any attention to it.
By the equivalence principle, the same thing would have to happen to a light beam in a gravitational.
So again, by the equivalence principle, some notion that, so because the light beam traveled in a dead straight line and the side of the ship moved away, that means on Earth the light beam has to be bent by gravity, okay, as much as the spaceship surface moved. Why would anybody think those two things have to be comparable at all? It's an insane expectation. It would be silly to think so.
Field. The light beam would have to bend.
So we have a truth about light, right? We kind of know. See, this all happened before they knew, that you couldn't bend magnetism and you couldn't bend all this other stuff that we found out is moving the same speed. So all the other stuff moving the same speed as light, magnetism and what's the other stuff? Light and gravity. Yeah. So those things, we figured out sort of what they're doing, and we figured out they're not affected by any of these forces. A force can't affect a force. You can't bang light photons into light photons. We can't crash two laser beams into each other and have the laser beams bounce off of each other. Just a fact. They have to hit matter. Forces only interact with forces. And that they are kind of new from gravity is that, my gravity, the gravity I create, has to travel all the way to the object. It can't travel halfway and say, oh, I can feel your gravity and therefore I'll bounce off your gravity. No, it has to go all the way to the object. The force can't interact with the force.
And toward the massive object generating that field.
All right, gravity can't bend light, light can't bend gravity. Just can't. Magnetism, nothing can bend it. Force can't affect force. You can only counter a force. So you can have a force in the opposite direction, but you can't, and you can, that's about it. Or you can add a force. You can add, subtract forces. But the forces themselves can't do the math. The matter has to do the math.
And that leads to the idea that massive objects are actually bending space-time around them. So light beams traveling through space-time sometimes end up on curved and bent paths. How about them?
Yeah, that's it. How about them apples? How about making a proof of it? Okay, you never repeated the Eddington experiment successfully. You never did it with better technology in 100 years. All the great technology we've had in the last 100 years, right? Just imagine all the technical advances. We went from a Model A, we went from, the Hindenburg. We went from just all the things we went from. So they haven't even attempted the experiment with better technology on Earth, let alone we've had all those satellites. She just showed them 2,000 satellites up in space. 2,000 of them. All of them probably with cameras on them, frankly, and it wasn't take much of a camera. The resolution in space is 400 times better. So you need 400 times less of a telescope to do exactly the same experiment. 400 times less of a telescope. I mean, you could do it with a flip cam. You could do it with a GoPro from space. And it's a fact. And they've never done it. But this is their physics, right? They're going to assert it as a truth, and the evidence record is glaringly absent. They don't have the evidence. They're lawyers at court, and they're citing, that piece of paper over there has a drawing of a gun on it. So you can imagine there could be a gun, right? His fingerprints could be on the gun. I mean, this is how bad their case is. And they assert this with such confidence and arrogance. I know some mathematics, so you should believe whatever I tell you. That's basically all they are. They're mathematicians. And they're basically saying, I know some math, therefore you should believe any story I tell you about creation, and the Big Bang, and expansionism, and singularityism, and the superpositionism, and then we have this special entanglement thingy, a little ESP between the particles. It's very special. Moves faster than the speed of light. Very special. It's a religion.
So that's today's lesson on gravitation and orbits. When they ask you what you learned on YouTube.
So you didn't learn anything you couldn't learn on a Wikipedia page in less time. So thank you.
Today, here are your two key takeaways. One, Newton's laws of gravitation. All masses attract each other with a force of F equals.
Right, they don't really attract each other. They're just consuming some energy. And you consume the amount of energy proportional to how much mass you have. So however much mass you have, that's how much energy you consume, and you consume it all over your surface because you're consuming it no matter which way it goes into you. It has to plow through that much matter. And depending on how much matter, like my hand right now, it's got very little mass in it, so the energy going this way is not creating a tremendous amount of gravity right over this way. All right, but if you go this way through my hand, okay, then it's 4 times as much mass. So there's more gravity on that side of my hand. And if I could make a hand in space, you'd see that. You could fly around the hand and you'd say, whoa, the gravity's really heavy over here. And then you get to this side and go, oh, the gravity's very light over here. That would actually happen. Actually.
GMM over r squared. And 2, orbital periods. The square of an orbital period is proportional to the mass of a thing being orbited and the cube of the orbital radius. So 4 pi squared over t squared equals gm over r cubed. Here's a recap of all the problems we did, because the best way to make sure that you get these concepts.
All right, so little problems, little mathematical problems, get the concepts right. So she introduced the concept of dark matter. Well, they don't have that in any of this formula, right? She introduced the concept of bent space and an equivalency principle. Well, where's the formula for that? Oh, that's right, there doesn't exist one. Yeah, so they don't have math or any of that crap.
Is to work the problems yourself. And for the problems we did in this lesson, like calculating the acceleration of gravity on Earth or finding the orbital velocity of the eye.
So these are all these problems are all problems Newton could do. So these are all problems from the 1600s. So, yeah. Didn't have anything to do with any modern math.
ISS, you can easily give yourself more practice by repeating them for other solar system planets.
Blah, 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 blah. Another commercial. Two commercials, of course. Blah, 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 blah. Trying to make their money.
The solar system, but the last bit of science I want to share is about exoplanets. There are other planets outside of the solar system that we have found, like Kepler 78b, which
Right, and it doesn't have anything to do with gravity, so again, this is just kind of like, what the fuck?
is a planet that orbits extremely close to its star at only 900,000 kilometers. And for comparison, our closest planet, Mercury, which is our closest planet, the closest it gets to the sun is 45.9 million kilometers. So Kepler 78b is really close to its star. Its orbital period is only 8.5 hours. And because it's so close, the surface temperatures reach 2,400 degrees Celsius, which is 9 times as hot as Venus. But in the next 3 billion years, the star's gravity will eventually suck it in and will completely
Right, so a lot of this they have to guess at it, because they have to guess at how big the sun is and how massive it is. So they guess one thing and then they approximate everything else based on that guess, and you know, there's a lot of guesses here.
consume it. So there's that. We also look at the orbital periods of exoplanets to determine the radius of their orbits, and from that we find planets that live in the Goldilocks zone for life, which is where water will be in the liquid phase. So you get to learn a whole lot about exoplanets and
Yeah, those are the special water. Just put a glass of water anywhere in space, and if the water stays liquid, life will happen. It'll just poof out of the glass all by itself, because water's magical. Water's a solvent.
more if you continue on in physics and take a class in astrophysics. I do hope you continue on the physics. And now here's
La
a
la 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 la. So yes, just do it in this trivial, silly way. Be motivated by silliness to learn a silly religion, and then you can pass your catechism, and then you can be an official pope and wear a hat. You know, maybe you can be the Pope of physics. You can have a funny hat, and you can have $10,000 shoes, and wear a dress.
message for you from a special guest. Hi everyone, congratulations.
So what the fuck is this shit? I don't even know what the hell this was tacked in here for. What's the deal? Why is this on here? What is this shit?
I'm finishing another amazing lesson put together by the wonderful physics girl Diana. So I just want to say,
So she did a commercial for me, and she's saying nice things about me, so I guess that's why I'll include it, because she's saying nice things about me. And she's all excited and girly too.
stick with
She has a little flower in her hair. Scientists do that.
it, because once you understand physics, it's like you have this whole superpower to see so many things in the world. I just
Yeah, all that you made up, a bunch of silly delusions about reality. Alright, so you're just part of the little, oh, once you find Jesus just fills you with love, 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 and oh, I love all the universe and the exoplanets, and so yeah.
want to say though, like on your journey, it's going to be really, really intense because, oh my gosh, there's going to be new equations, these
Oh my gosh. Equations. Yeah, that's all there's going to be. There won't be a single concept. You won't have a single concept right because you haven't figured out anything since Newton. And just as Einstein said 2 years before his death, I have spent 50 years, analyzing photons and have not improved my understanding one iota. That's what he said. Okay? Right. He spent a lifetime studying it and didn't figure anything out. Just a sad commentary. And you don't know any more than he does, which is nothing. You haven't advanced human understanding at all. All you've done is told silly frickin' stories and wasted billions of dollars on experiments that have no hope of getting to the truth. Your colliders and your LIGO magic mush.
concepts, a bunch of people's names associated with different laws of whatever. So you know what? Just ask.
Laws of whatever.
questions. Like, it's going to be really helpful for you. It'll be helpful for other people. Ask them in forums, find different friends to talk to, watch different videos. Like, just keep at it because it's great. So stick with it. You got this. I'm Dr. Brittany Kamai. I'm an astrophysicist. I work on building instrumentation.
So all these doctors seem to be astrophysicists. That must be the easiest doctorate to get because it's all mush. Yeah, you know, just mush.
To study the universe, specifically gravitational wave detectors.
There you go. See, so yep, just part of the network of bullshit. So, will you answer any of my questions? I haven't found anybody willing to answer my questions. I'm attempting to pay people to answer my questions. Will you answer some questions for $1,500 on Physics Girl's channel? I'll pay you $1,500 to answer a few questions.
Ripples in space-time, and I think about how to make these detectors even better by using this other
Yes, by doing some other, just complete bullshit science.
cool thing that's on the scene, which is metamaterials.
Yes, we'll use metamaterials, and that'll make it so much better because we know so much about how they function too. No, you don't.
People design materials, defying what we thought of physics before. So good luck, put in the
Yeah, defying what we thought of physics before, or whatever that meant. They're defying physics.
work. Can't wait to see what comes out of it afterwards. Take care.
I have no idea why that was in there. What the hell was that for? What? So, lead writer. So, she was a writer, but there was a lead writer also. Yeah, she has a whole list of people. A whole list of people in here. A whole bunch of people. Anyway, look at all these people. For this. Horrible physics. But I guess the next Veritasium video is going to be the Slinky video. I don't know. I didn't see that one. Maybe it's from a few years back. Who knows? But whatever. All right. So enough. Made my point. Horrible physics. Horribly evidenced. Horribly underproven. Horribly bad to be asserting this as, oh, we have the facts. We've done our jobs. You haven't come close to doing your job. Of compiling a good argument, and it's just shameful that you're too much of a coward to defend any of that crap, and that none of you have taken any time to recognize that, well, if you think about it, there's lots of alternative explanations that work better than your explanation. So anyway, till the next time and such, so forth and whatnot.